in the minimal symmetric standard model. So in the hope that we could actually make a contact with particle physics already in the near future. So the basic message here is that if you look at the one of the flat directions of a minimal symmetric standard model, and I will explain what those flat directions are. You can use flat direction, the field that describes such direction as the interval. So my claim is that you actually get the correct number of e-folds, the correct density perturbation, and so on. And in order to achieve this, you need to have a saddle point along that flat direction, and that saddle point requires a certain fine-tuning among the parameters of that rate supersymmetry. And I shall discuss how that apparent fine-tuning could actually be removed if you consider supergravity models of certain class, so that you can actually get that kind of inflationary potential within the MSSM from the Gauss potential that turns out to have a form that is often found in certain string theory quantifications. So that's the sort of the outline and the main message here. So let me first try to describe what is MSSM inflation, how does that arise, and the motivation for all of this is that inflation, of course, is a great idea, as Andre just told us, but of course we also heard that there are many open questions. There is the question of what is the particle theory origin of the inflation. How is it related to theories that we know and very much cherish, such as the MSSM? Usually inflaton is assumed to be a gauge singlet because a non-gauge singlet would have interactions and would be subject to radiative corrections that could easily and that indeed will easily spoil the flatness of the slow roll potential. However, the disadvantage of choosing a gauge singlet is that it's not really motivated by any particle theory other than particle string theory, and there is a debate going on whether that can be counted as particle theory. So, as far as we know, there are no gauge singlets in nature. And then another issue that was already referred to here was how do you couple the inflaton to baryons, because eventually it's 50K to baryons, and of course there are many phenomenological recipes for doing that. You take the inflaton and say that it's coupled to some other field, and that coupled to some other field, and then you have a sort of a chain of almost cyclical proportions, and down the line you finally find baryons. But you would like to have this coupling of baryons to be dictated to you by the structure of the theory rather than something that is within by hand. And the third motivation, which is perhaps more philosophical, is that if the inflaton is a singlet field, it's probably difficult to have any testable consequences in the lab. So using particles for light experiments. So one can certainly describe the inflation with a single scalar field, the properties that you see in the CNP, but there will always be this lack of an independent separation from what we could usually term as non-physics. And MSSM, of course, has the great virtue that it has a number of scalars. It has its leptons and quarks and Higgs. The scale of the MSM is very low, and of course, for this reason, people have usually dismissed MSSM as a possible candidate for inflationary phenomenology. All the field values are much less than Planck scale, and because of this low field value, in order to the perturbation of the correct amplitude, which go like the scale of the theory divided by the slow roll parameter epsilon, you need an extremely flat potential. But then you would worry that because of this flat potential, this radiative correction will spoil your slow roll inflation. And clearly, if any random field that you take from within the MSSM cannot give you inflation as such. You need some extra protection for the potential to be very flat. Now, fortunately, supersymmetry together with gauge symmetries actually give you very flat direction in the space of scalar fields of the MSSM. There are directions so flat by virtue that they actually have a completely vanishing potential in the limit of X supersymmetry. So this is a sort of a mathematical fact. And there are, you could say that there are good news and bad news in that the bad news is that there are quite a few of them. There are something like 300 flat directions in the MSSM. So how you find them is that you look at the globally unbroken supersymmetry that consists of the potential that has an F term and a D term. I can point. So there are the two parts that go into the potential of the MSSM potential for the scalar field, the F term and the D term, and the flatness of the potential requires that both of these terms, the F term and the D term, are separately vanishing for all field values. Now, the space of fields of the MSSM has a dimensionality of about 49, and these flat directions, they are certain trajectories in the space of fields, which exist in the limit of unbroken supersymmetry. These directions carry global charges, and that can most often be associated with the baryon number or the lepton number or some combination of the baryon and the lepton number. So there are all 300 of these, and this is the bad news. There are many of them, but the good news is that all of them have been classified. They can be classified in terms of operators that describe the field content of those directions. I won't go into any detail. If you want to read about these things, because there are reviews and things that will tell you how these directions are constructed. Now, if you can consider these flat directions in the presence of gravity, and of course, if you are interested in inflation, you need to consider gravity. The gravity is not normalizable, and therefore all of these directions, all of MSSM must be supplemented by non-renormalizable terms, because that are allowed by gauge symmetries and supersymmetries. So when I'm interested in gravity, I'll need to add along each of these flat directions all the possible non-renormalizable superpotential terms. And again, the good news is that for all of these flat directions, people have classified what sort of non-renormalizable terms are allowed by gauge and supersymmetry. And the lowest cloud has a certain definite dimension. That definite dimension depends on the dimension, on the flat direction. So that is one aspect. There are non-renormalizable supersymmetric terms that lift the flat direction, that is, make the potential non-zero. And in addition, of course, we know that supersymmetry is working softly in the nature. So there are two kinds of contributions that this flat direction receives as far as the potential is concerned. So there are soft supersymmetric breaking terms, the usual mass term. There are soft breaking terms, the A terms, that relate to the non-renormalizable terms of the potential, to the F term. These are typically operators that have some dimension n. So all of these flat directions have been shown that they are lifted by operators that have dimensions less than 9. So all of these things are known and are practical. So now you can write down a potential. What does the potential look like in the field space of the MSSN if you're looking at along these flat directions? So these are complex fields, so there are a field modulus, and then there is a phase, and then you have something that comes typically from this supersymmetry breaking A term, and then this is the F term squared that comes from the non-renormalizable superpotential. The interesting feature here is that because of this A term, there is in the complex plane of this flat direction field, there is an n-fold set of minima, and the lowest minima is obtained whenever this cosine here in front takes the value of -1. So in that fashion, you get a secondary minimum along the slope of the potential. So the origin is the absolute minimum, but then along the slope there will be another minimum provided a condition holds for between the A term, this is some number which as far as I'm concerned, is unknown as of yet, and this is the max. So there is, if such a condition holds, there will be another minimum. So the potential looks something like this. There is a global minimum here, and then if I move along the flat direction further away from the origin, there is another minimum with a barrier there. And you might think that, okay, perhaps I could inflate by sitting here in this minimum behind the barrier, but then we will be back to the problem of old inflation, that the inflation would never end. So then one notices that if there is a certain relation between the A term, the supersymmetry breaking A term, and the supersymmetry breaking mass term, then this barrier actually vanishes. And the potential here becomes very, very flat. It becomes a saddle point where the first and the second derivative of the potential along that flat direction vanishes, and the potential in the vicinity of the saddle point is given by the derivative of the field along that flat direction. So if you make that assumption, it turns out, and I will not go into details, that you can actually pick one of these flat directions which are either purely leptonic or purely baryonic directions that are listed by dimension 6 operators. So then, if I choose that direction, I will find sitting as my only input now is the mass, the supersymmetry breaking mass, which I choose to be about of the order of 1 keV. I have chosen the direction with the n equals 6 direction, dimension 6 operators. My theory parameters are now related because I've chosen them to be related. There is one coupling constant which I now take to be for the purpose of demonstration simulation model 1. And then I will find that the inflation takes place at a very low scale, at a scale of 1 dB roughly, with a value of this field much less than the Planck scale, about 14 dB. Now, in order to have a global inflation, this saddle point condition must hold very precisely. You cannot allow for large deviation from the saddle point, otherwise the global inflation does not take place. And I will come to this fine-tuning in a while. Now then you just go on, you have this potential, you go on and you compute in a usual manner what sort of inflation you get. You get a perturbation amplitude which is 2 times 10 to the minus 5. You get a very small epsilon parameter and a spectral field which is about 0.92. There are no gravitational waves, of course, because it's a very small inflationary scale. So I will emphasize the fact that the only thing I've done is I have chosen the saddle point in the space of this MSSM back direction. And the only input parameter here is the scale of supersymmetric space. So no other extra scale is involved. The only thing is the supersymmetric scale, which we basically should know. Okay. So it seems that if I can make that assumption about the existence of the saddle point, then I will get something that is very close to what is actually observed in the cosmological form. Of course, if I deviate slightly from the saddle point, I can get slight deviations from these numbers on the spectral indices and so on. But let me now, for the purpose of this talk, just focus on the assumption that we actually have exactly the saddle point. Now, the virtue of this kind of model is that there is now actually a connection between the inflaton sector parameters and the particle masses for it. So if I choose, if I have a NLE flat direction, I have an inflaton, its mass is now given like this, some dependence on this parameter lambda. Now I can run down this mass from 10 to 14 GeV to 1 TeV for lighter energies to find what is the mass of the selectron. So the mass, because this inflaton now is a combination of selectrons, its mass is related to the observable masses of say selectrons. And so if LHC is very long mass selectrons, then for sure this model can be ruled out. Another example of connection to particle phenomenology is that if because now the inflaton is part of the MSSM, and presumably dark matter is also part of the sector, the values of the inflaton field, the values that we have for the say electrons or for the quarks, they are also related to the masses of dark matter particles, the neutralinos. Here is one example. Here is a slight deviation from the saddle point condition is allowed here. Here are the inflaton masses. Here are the spectral indices that one would get, and here is then a plot that shows where is the allowed region for dark matter. So this assumes now that there is a certain initial conditions, the minimal supergravity initial conditions for the parameters of the MSSM, so that you can run down the renormalization equation to LHC energy. You put in here all constraints that you have for these particles, for the masses, for the soft-breaking masses, and for the gauge masses, and here you have now lines that correspond to cosmology. So certainly you can make contact with usual particle physics and cosmology in this kind of way. So then there is question of radial directions. This is a single field, but this is not. It's a gauge. It's not a single field, but it's a gauge invariant field. There will be there will be some radiative corrections, and if you look at the one-loop radiative correction, you will find some shifts for supersymmetry breaking parameters of the order of 10 to minus 2, but perhaps the important basic theory is that even after these radiative corrections, the existence of the saddle point is not removed. That saddle point remains. Now let me address the interesting question that what actually then fixes this saddle point condition? What fixes the relation of A and M that is required here in order to get inflation in M to M? And because A and M are just soft supersymmetry parameters of the theory, there is no explanation for them, for their values within MSSM. And one needs to move beyond MSSM, and one needs to, that obviously means that one needs to move to supergravity. So I need to write down the supergravity potential, which many of you know, looks like this. Now there is no D term because I'm looking at the flat directions, they are D flat directions of supergravity. So the potential, supergravity potential is given in terms of a Gale function of the Gale metric is now basically a function of some hidden sector and some observable sectors. Now the math term is then for this supergravity potential, it is the second derivative of the potential at the minimum of the hidden sector, and the term which I now call A6, the A term along this flat direction, that would be the sixth derivative. Now, of course, you could relate these two things by some chance. It just happens so that at the minimum of the hidden sector, when the hidden sector field states are there, these two parameters are related in the fashion, in exactly the fashion that I would like them to be. But that's just chance. So what I want to require is that I get this relation, the saddle point condition, so that it is not an accident, but it is true for all the values of the hidden sector field. So this means that, of course, that I'll have to look at the form of the Gale potential. There will be some moduli fields, fields which can take any value, and I still get this relation. So saddle point relation. And the question is it possible to have a Gale potential of such form that this MSSM inflation arises identically? That I get it automatically without really doing anything. So what I want to do then is to assume that I have a superpotential. So now I'm looking at this flat direction. There is some hidden sector. There is the flat direction that has a superpotential that shows like 5 to 6. There could be also higher order terms. I have a Gale potential that I write in this fashion now. There is a part that depends only on the hidden sector, and then there is a part that is an expansion in this flat direction field. And then the question is, does there exist a Gale potential such that this saddle point condition, and therefore MSSM inflation is obtained automatically? And now comes a word from our sponsor to answer is yes. There exists such scalar potential. And I will show you how to get that by construction. So I will construct a scalar potential that produces energy inflation automatically. So I write down the scalar potential and expand the lowest order. I will get the energy potential, but there will be some corrections which I now just going to schematically write as higher order corrections to that potential. So I can find all of these coefficients. They are complicated expressions in terms of the scalar potential of the hidden sector, and then the coefficients that in the scalar potential that multiply the direction dependent parts, and there are derivatives and so on. Then I can find out all of these, what is V6 and so on, and find that I can impose then the saddle point condition. The saddle point condition is some condition that these functions in the scalar potential to satisfy. These are partial differential equations of two unknown functions. So I will assume now that the lowest order term, the cosmological constant is zero. I have no explanation for its vanishing, but I will set that here cosmological constant. So if I do that, I can then find this saddle point condition looks very complicated and it is. But let me start by making a simple assumption that there is only one hidden sector field. And then assuming that K and Z2 are independent functions, I actually can find the solution. The solution for K looks exactly like in the no-scale supergravity, and the part of the lowest order part, the phi squared term coefficient, can be solved in terms of the hidden sector field, and it looks like that. Now this is an example of a scalar function that actually gives me energy inflation potential in the leading order without any other adjustment. Now, so this was for one field. Now for several fields guided by this, let me then try an ansatz where I have a term like this, and then here I have hidden sector part multiplying phi squared with some coefficients which could be called modular weights, because these are the types of the scalar potential that often appear in string classifications, like for instance the Italian multipolar classification of the heterotic string. So in terms of these coefficients, the saddle point condition is an equation like this, where alpha and beta are sums over all these modular weights, and the weights of the beta is actually, or minus beta is actually number of moduli fields in the string context. So if I solve that and now look for solutions that are rational numbers, taking my cue from those string classifications where we have rational numbers, I will find the lowest order solutions as given in here. So beta minus 3, I choose alpha, the sum of the modular weights at 3 minus 4 divided by 9, and so on. So there are also values of beta much higher, but I will not show them. So these are some values, and which very much look like the solutions found in the Euclidean multiple classifications, but in fact exactly these numbers are do not appear in the link. There seems to be no Euclidean multiple classification at this time. Okay. So now then I also worry about the higher order stuff. So I have only looked in the lowest order expansion in phi squared, and I should make sure that if I look at the higher orders in phi squared in the scalar function, that I will not spoil the flatness of the energy inflation potential. I look at order by order the small changes in the potential. It turns out that I only need to look at the first two non-leading orders, and so that I must consider also the expansions in the Shannon potential to be consistent. So I find that I impose the saddle point condition, I impose that the flatness is maintained, and find out that the higher order terms, they are so like Z2 squared, the lowest order squared, the lowest order cube, so that actually this is an expansion in the canonically normalized field, which is square root of Z2 times pi. Now these coefficient relations, they are determined by those plates, modular weights, and the number of other parameters alpha n and theta n. And so in its full glory, you can find the full solution. So to order 5 to 6, there are some coefficients mu and nu that depend on these betas and alphas, and you have a table that looks like this. So for sure, this is a proof of existence that you can have a Kähler potential. If you have a Kähler potential of this type with these coefficients, you will get inflation within the MSSM for free, so to speak. And it would be interesting to find out whether any of the string multiplications actually would give Kähler function like this. So let me conclude by just mentioning one thing, and this is something which remains to be done in great detail. Because the Kähler function is now fixed, then there will be many implications for particle phenomenology. For instance, if I now take a non-flat direction, which I call psi, that has a renormalizable superpotential, I plug that into the Kähler potential, and I will find a linear eta, which is something that actually can be measured or at least constrained phenomenologically at LHC. So I will find that there is a relation between A3, the linear A term, and the mass of this non-flat direction M phi that depends on these alphas and betas. And this is of course something that again serves as a constraint for cosmology that can be hopefully measured at LHC, of course by doing the renormalization of this analysis. So let me conclude now that it really seems that n equals 6 MSSM flat direction do have all the ingredients that you need for having a successful inflation. In this picture, we insist on unification variant combination, quark or lepton, but the existence of inflation requires a double form and with an instant fine tuning. But one could hope, and as I have shown you, one can actually get that fine tuning from a class of Kähler potentials that are expansion in terms of the canonically normalized flat direction field. And then the question remains whether that kind of Kähler potential, really, as I mentioned, whether it corresponds to any string multiplication, and indeed whether that string multiplication would actually give rise to MSSM. And the virtue of this kind of a scenario is that almost everything is calculated. There is nothing to tune, nothing to fiddle about, and moreover that the parameters that we have in the integral sector can in principle be determined in the laboratory just by looking at particle phenomenology. So either this model falls or wins, there is no middle ground.
First, with regard to the scalar potential, there is this quite generic in the fact that you call log of h bar of h bar. With regard to phi squared powers, I don't think. So there are features which are generic but the potential in phi squared is not clear. And my question is, we have r equals 0 and ns 092. Is it not almost marginally ruled out? I mean, 92 is 2 or 3 sigma. How much?
Well, I think so this was a, okay.
You explained that the starting point is really 92.
The third, well, but that also includes some small minor modifications due to supergravity. But even for getting that, I think 0.92 is 0.95.
Oh, so you consider that they're still inside the...
Possible.
But after Planck, it can change.
Well, we'll see. Yes. It can be separated, but it can be ruled out actually.
Esistevo di tre potentiali per all because the third potential is like but then the third potential is not affected by quantum correction. This is the quantum correction. But
yeah. Yes, that is. Yes, I did not address. I mentioned that there will be one loop corrections and two loop corrections and so on. So that those will shift the shape of the potential somewhat, and that could be a problem. That certainly will shift the values of A divided by N. So I have no good answer to that, except perhaps the hope that for some reason that I don't see at the moment, A over N could be a renormalization could be invariant. Yeah. Yeah, but there are many orders, not the lowest order.
Another question about the dynamics. What mechanism do you have in mind which will put the scalar field initially at the south?
Yes, that is of course. So I've always assumed that initially my field just happens to be at the certain point. And of course I have no good reason for that. But I think this is a generic problem in inflation, the initial condition. And I could now, of course, sort of wave my hands and say the magic word, landscape, and so on. But so I don't really know. I just assume that for now I could assume that initially I'm at the vicinity of the saddle point. If that happens, then inflation will follow.
Maybe just a comment to answer Robert's question. So the linear system, it is possible to get a web of inflation. So you can construct similar thing like what you get like a landscape, but not exactly a huge landscape, but along one flat direction, along another flat direction, you can construct false minima. And then you can imagine that you're turning, so you have inflation one after the other, and then the last stage of inflation is given by either A or B or U to B kind of that. So that's one way to address the initial condition problem.
If you go beyond the analysis, for example, if I have to say that having a not just a lot of do you think the value can still be
Well, certainly, I mean, for all gauge groups, I think generically you will have some saturation. Whether those saturations for a generic gauge group are such that they actually produce the correct density perturbation and the spectral index, but I don't know. But sure, I mean, I guess the answer usually is yes.
If we go on to the next